In this lecture, we'll be talking about Norton's theorem. And if you haven't watched the video lecture yet on Thevenin's theorem, I would suggest you watch that one first, because Norton's theorem follows a very similar procedure, and it's explained in a little bit more detail in the video on Thevenin's theorem. So in this video on Norton's theorem, we'll just be moving just a little bit faster, assuming you've seen the procedure already before. So one of the important things about Norton's theorem is, just like for Thevenin's theorem, this only applies to linear systems. Right? So your system has to be linear for you to be able to apply Norton's theorem. But the principle is the same. You basically have an electrical circuit, and you're going to replace it by an equivalent model. So remember, this equivalency means that electrically they behave the same. So no matter what I attach here at these terminals, this model here will behave exactly the same way. So it's just a simplified version of my original circuit. But where for the Thevenin theorem, we basically had an equivalent model that consisted of a voltage source and a resistor, for Norton, we have a current source and a resistor. To be able to calculate these two elements, the current source and the resistor, we actually follow the same procedure. So we're going to consider these equivalent circuits, and basically we're going to use that equivalency to figure out what is IN and RN. So equivalency means that electrically they behave the same no matter what I attach between the two terminals here. So let's first not attach anything and look at what happens when we leave these two circuits in an open circuit configuration. So in an open circuit configuration, I know there is zero current here, and so I can calculate the open circuit voltage for my circuit. Now, what's the open circuit voltage for my Norton model? Well, again, there is zero current here, so all this current from the current source is flowing through Rn. So the voltage that appears, it's nothing more than this IN times Rn, and these voltages have to be the same. So IN times Rn has to be the same as the open circuit voltage I calculate here on top. That's one thing I can do. I can also look at if I attach a short circuit over there. So I make it a short circuit. In that case, I'll have a short circuit current here. Now, what is property of a short circuit is that there is no voltage drop here, right? There's zero voltage drop here. So this V is equal to 0. So when there's zero voltage drop over my resistor, that means that there's zero current through my resistor. So all this current IN is flowing through this branch. So my short circuit current for my Norton model is IN. And that short circuit current has to be the same as short circuit current here. So when I take my circuit, my original circuit, make it into a short circuit here between those terminals, and I calculate what's this short circuit current, that has to be equal to this IN. So IN is equal to the short circuit current. And then finally, I can also look at the equivalent resistance seen between these two terminals. So I can look at the equivalent resistance seen between these two terminals, and to calculate the equivalent resistance seen there, I basically need to set all dependent sources equal to 0. That means that current sources become open circuits and voltage sources become short circuits. Well, so that's what I'm doing here. And then I can look at what's the resistance that I see looking into that terminal. So for the Norton model, it's just Rn, that's the only resistance there. For my more complicated circuit, I can calculate the equivalent resistance by applying what I know about series and parallel connections of resistors, or I can apply a test voltage and look at the resulting current. And we've talked about that procedure as part of Thevenin's theorem. So that will allow me to calculate this Rin, and that has to be equal to Rn. So in summary, I have an unknown circuit here in my box. If I calculate the open circuit voltage, the short circuit current, and the resistance seen looking into those terminals, these have to be equivalent to those same quantities that I can calculate for my Norton equivalent circuit. And so I can get these three equations, and with these three equations I can find the two unknowns, which is IN and RN. So for any circuit, any linear circuit, I can calculate what's the Norton equivalent model. But again, this only works for linear circuits. So just like Thevenin's theorem, Norton's theorem is a very powerful way to simplify circuits, and it's very useful when you attach different things to the same circuit. So you don't have to calculate everything from scratch. You can just use Norton's model, just like you can use Thevenin's model.